All right, next problem here. I want you to evaluate the closed integral over C of y squared dx plus 3xy dy, where C is this region. Notice I'm going counterclockwise around it. Um, uh, a circle, radius 1, radius 2, but only the top half. So uh, I just before I tell you to pause it, I would not parameterize this one. The trig work would get complicated. Instead, I would go Green's theorem. Anytime we see a closed integral, you might want to think Green's theorem just because, and like you say to yourself, how easily could I integrate over that region? And um, you should see that this one is one for which the region is not too bad to define. So pause, do it. And I'm going to show the answer. We'll just go like this. Okay, so you can see, I'll come down here. I got 14 over 3. So if you got that, great. You can skip the rest of what I say here and go on to the next problem. Or if you got it and you want to listen to me, then you can listen to me talk about this too. If you didn't get that, then I'll walk through the whole thing. So first thing I'm going to do is find the appropriate partials. Oh, sorry. This to me screens Green's theorem because it would be really easy to define this region in polar. I would go 0 to pi on my thetas and then 1 to 2. If that's something that I can do, I'm typically going to try Green's theorem. So remember, m is this x component, n is the y component. This right here, n sub x minus m sub y, that is the curl. So Green's theorem says that this integral is the double integral over this region of the curl of that vector field, boom, comma boom, dA. So this sub x is 3y. This sub y is 2y. So when I calculate the curl, I get 3y minus 2y, which is just y. I left the r and the dA just because it's more simple to do that at this point. From there, I'm going to recognize that I want to go into polar. This y gets replaced by a r sine theta. And then my dA is r dr d theta. My r's go from 1 to 2. That takes me at any point from this spot to that spot. And then I'm going to span that gap from 1 to 2 on the radius from theta equals 0 all the way around to theta equals pi. From there, I simplify a little bit, just getting the sign out of the way. I'm going to do my r integration first. R squared comes from this r times that r. That integrates to 1/3 r cubed, evaluated from r equals 1 to 2, which gives me 7/3. And then that was that integral, and I just moved it out front because it was a number, and I can do that. I'm just getting it out of the way. And then what's left? My integral from 0 to pi of sine theta d theta. So what's sine integrate to? Integrates to negative cosine theta. I'm going to evaluate that from 0 to pi, and I'm going to get negative, and then 7/3, and then -1 is the cosine of pi, because I'm over at an x-coordinate of -1, minus a +1 is the cosine of 0. So that gives me -2, multiply out there, I get 14/3. Okay, second problem of this little video here. See how many we can get into 15 minutes. I want to do the closed integral of f dotted with dr. Should have vector signs over top of that. With vector field x minus y cubed, comma y cubed plus x cubed. And C is the following quarter circle of radius A. So I'm in that first quadrant up there. I'm going counterclockwise. So see if you can set that up and then do the whole thing. Here's my answer. I got 3 pi a to the 4th over 8. If you got that and you feel really solid with that, great. If you didn't, and you should listen to me walk through it so you can see how to do it. Or if you got it and you just want to hear me talk through it, then you can listen as well. All right, so once again, just like the previous one, this thing sort of screams Green's theorem in polar to me. So I'm going to try that instead of trying to parameterize with thetas and like 3 separate paths, right? So I've got 3x squared plus 3y squared is my curl. The n sub x is the derivative of this with respect to x. This goes away. This is my 3x squared. My minus m sub y is this thing partialed y, which that goes away, and then this gives me a double negative, one from here, one from there, on a 3y squared. So my integral of f dotted with dr is, that region there is 0 to pi over 2, and then 0 to a. And then this mess right here is x equals r cosine theta plugged in here, and y equals r sine theta. Those are my polar conversions from rectangular to polar for x's and y's, plugged into there. So I get 3, the r gets squared in r cosine theta, and then the cosine squared gets squared in that cosine theta, whatever. And then the plus 3, the r squared, and the sine squared. So it looks really messy at first, but you have enough experience with all this stuff that you should say, oh, cosine squared, sine squared. I think I can get rid of that stuff. Let me do some factoring. So when we do that, I get a cosine squared. I basically pull a 3r squared out of this and out of this. I get a sine squared plus cosine squared, which that's 1. And then I'm left with 3r squared, that's this, times that r, gives me my r cubed. So really, I've got this integral that's pretty simple to do, because I got rid of all my messy trig stuff. So integral 0 to a, or sorry, integral 0 to pi over 2, integral 0 to a of 3r squared dr d theta. Come down here. That gives me the 3r squared, sorry, the 3r cubed integrates to 3 over 4 times r to the 4th, evaluated from 0 to a, from r equals 0 to r equals a, with a d theta. That just gives me, the 0 is convenient, just gives me this plugged into that, which gives me 3a to the 4th over 4. And then I need to do the outer integral from 0 to pi over 2 of that. That's simple because I just, it would be this times theta evaluated from here to here, which the 0 goes away. So the pi over 2 just gets multiplied by this piece right here, and I get 3 pi a to the 4th over 8. Okay, last one of these. We're on page 5 of 5 here. I'm going to take the same vector field as the last problem, but I'm going to do a new region. It's going to be rectangular, corners at 0, 0, 2, 0, 2a, and 0a. And once again, we're going to go counterclockwise about this region. So pause it, see if you can do it. I'm going to show the answer. I get 2a cubed plus 8a. So let's come down here, or up here. Just to have it up here again, there's my vector field. This is what the path looks like. I start at the origin, go out, go up, go over, go down. This could be done directly, potentially, like moderately quickly, because all of the dx's and the dy's would be 0. Maybe that would be a good problem for me to give to you or to do. calculate each of these pieces on their own. But we're going to go ahead and do it with Green's theorem right now. The integral of f dotted with dr is the line integral, closed line integral over c of f dotted with dr is the double integral of the curl of f dA. So first thing I got to do is set up my region. This is not polar, it's rectangular. I'm going to go 0 to 2 on the x's. That gets me from here to here. And then I'm going to go 0 to a on the y's, and that gives me this rectangular region right here. This curl is the same as the curl from the previous one, so I'm not going to talk about where it came from. But then I get dx and dy. Did I do that? This should be the other way around. It should be a dy and then a dx, because the 0 to a is the y range. So hopefully I did that correctly. Oh no. Man, that had been going so well. I am so sad. But I'm actually not that sad because I still got the same answer. I think it's because of all the symmetry with this. Here the math is correctly written, I think, I hope. So I need to integrate with y first and then x. So if I integrate with respect to y first, this goes to 3xy. This becomes power rule y cubed, evaluated from y equals 0 to y equals a. And then I got a dx on the outside. That makes this an a and that an a. So I get 3x squared a plus a cubed with a dx. And then from there, I get, I integrate that with respect to x. So this goes to ax cubed right there. And then this goes to x times a cubed. And then that gets evaluated from x equals 0 to x equals 2. And then it would be flip-flopped if I had gone directly from here to here. But I left the old answer that was there. I get 2a cubed plus 8a. So hopefully you're feeling pretty good with Green's theorem and with direct parameterization and all this stuff. I might make one more video related to this problem. But anyway, hope you're doing well. Hope this is starting to come together well. And please let me know how it's going. Okay.